So my name is Fred Simsac. I come from Poitiers in France, and I talk about symbolic computation for Bergman kernel, which is an area of complex analysis.
Thank you very much. I want to present to you some symbolic computation for complex analysis. Okay. Okay, it's mathematics, and if you consider the gamma function, the aim of this talk is to try to compute this multivariate power expansion of this type. In this sum, P1 and PM are parameters. Okay, there is a mathematical motivation. Yes, motivation. So it's about complex analysis. If you consider a smooth domain and you denote by A2 of omega the Bergman space, which is the space of integral function, there exists a reproducing formula given by that. And the kernel B of Z and W is called the Bergman kernel, and I consider the Lebesgue measure. And we have to know that this kernel is a main tool in the theory of complex several variables. You can see in the books of Krantz, Rudin, and Zhu. Moreover, if you consider parameters P1, PM in N star, and you consider this domain is called egg domain in CM. It's also called ellipsoid domain. Okay, we have the following result that for such domain, the Bergman kernel has this expression. Okay, what function? In this note, I will use mainly three mathematical functions. I consider the integrate because I will compute L2 norm of function. I also use the function sum because I want to transform power eigenfunction. And also, I'll consider hypergeometric function because when you work with the gamma function, you often have hypergeometric function. And how I will proceed to compute the Bergman kernel, I will use the general property that when you know a complete orthonormal basis of the space, then you can always write the Bergman kernel as this sum. Okay. Let's first consider a very simple example, the unit disk of C. In this case, I consider the power function Z to the power N, and you know that this is a complete orthogonal basis for the Bergman space A2. And the norm is given by this integral. If I compute the norm, Mathematica gives this with no problem. And with the general property, I obtain the Bergman kernel like that. You start with the power expansion, and directly you have the solution. I want to do the same thing for more complicated domain, and especially for egg domain. What is egg domain in C2? Okay, I consider two parameters, P and Q, and I consider the domain omega PQ given by that. And if I represent the boundary of this domain, we have something like that. I've a small. I want to evaluate this. I'm sorry, but okay. So what we know that. How do I evaluate the cell? Sorry? Shift. Shift? But shift gives this. So it's no problem. So what we know that this domain is interesting because we know the boundary of this, and the limiting domain is the unit polydisk in C2. So, and if I want to compute the orthogonal basis, I consider the same method as in the unit disk. So the integral is a little bit more complicated, but we have this kind of result. And it remains to use this famous relation here to obtain the value of the norm. So with that, we can compute the Bergman kernel for this domain. I first consider the case when p equals to 1 and q is an integer. In this case, I start with the power expansion like that, and the computation is direct, and I obtain this formula. But if I want to do the same thing for the domain omega 2, 2, which given by this formula, Mathematica cannot evaluate this term. So we have to recall the method in Valencourt. First, I consider a simplification, so I denote by E n1, n2 this fraction, and I create this kernel. The kernel S and the kernel B are related by this relation. And because of the 2 at the denominator, I split S of Z and W in 4 parts. And it remains to evaluate each part. For S10, S01, and S11, the computation is direct, and we have this. But for S00, the idea is to compute this function. If we write this function as a power expansion, and we concentrate on the coefficient, and we remark that this coefficient is in fact 0 whenever n1 and n2 is greater than 2. What we have is, in fact, if you are n1 here and n2 here, the red point gives 0. So this function is only the pink part, which is a polynomial, and 2 sum, the green one and the blue one, which are symmetric. The pink part gives this. And for the green and the blue sum, we first compute the coefficient Fn, and we deduce the function associated. So everything is finished. Finally, S00 has this form, and if we have all kernels, we deduce that the Bergman kernel is given by this formula. Okay, I mentioned that this expression has been obtained independently by John Duparc in 2008, but the method here has an extension. So if you consider any value of P and Q, and the general ellipsoid given by that, you can compute this kernel, but you have the solution in terms of hypergeometric function. And as an application, I want to talk about the Lucacan conjecture. And I give first the definition. If you consider a smooth domain, you say that this domain satisfies the Lucacan conjecture if its Bergman kernel does not vanish in omega times omega. If you look at the disk, B of Z and W has this form, so obviously it cannot vanish. Remember that we computed the Bergman kernel for this domain, and if we assume that this is not Lucacan, so this part may vanish inside, but by standard arguments, you see we have obtained a contradiction, and we deduce that is also Lucacan. Recently, Stephen Krantz proved that all ellipsoids are Lucacan. So if we consider our Bergman kernel for omega 2, 2, I passed the value here, and I want to minimize the modulus of the function, and finally, I obtain this. This is far from 0, so we can conclude that omega 2, 2 is Lucacan. And to finish, I want to to go for a development, what happens if you consider 3 variables? In this case, you consider the domain omega PQR, given by that. The related Bergman kernel is given with this formula, but the computation of the kernel is still open. And thank you very much.